want you to know that if it says the test questions will be very similar, but I might do a little twist. So don't expect them to be multiple choice, all of them, or exactly that same format. So I might ask you to show a mechanism, or might ask you some additional stuff, just to make sure you understand. And that's what I'll do today, kind of go through, not only answer questions, but kind of show you some mechanisms around each of these questions. So my first one that I picked, and it's not that, the others are not important. I'm just telling you that there's a limit in how much I can do. That's the reason. So I'm going to start with number 55. Okay? Question number 55. Chapter 10, of course. So make sure you check it. It's chapter 10, which is page 503. And my advice for studying is to study with groups, please. Don't study on your own, even if you're super smart. It helps when you help others to really get it better, okay? I can't emphasize this enough. Okay, so the first one is they want the product of each of the following. So in here, I'm going to go a step further, show the mechanism. This way we do two for the price of one, kind of, just do two things at once. So what are the product for this? So we have CH3, CH2OH, and asked to react with methane sulfonyl chloride. So what is methane sulfonyl chloride? The sulfonyl chloride is SOOCl. And the methane here, which is CH3. Okay? So first step, it says methane sulfonyl chloride. And the second step, methane sulfonyl chloride. The second step is CH3 C double bond CO. 1 second. I think I'm doing something. It's been a while, so that's why I'm kind of like, okay, wait a minute. So what should happen here when we have methane sulfonyl chloride? First, the Lewis acid, you agree? So here we have a Lewis acid. So the lone pair attaches here. So first step is activation, and then the chlorine goes. Remember we did this before? Yeah. So you have to have the Lewis acid attached to the OH, and then chloride goes. So we have CH3, CH2, CH2OH plus, and then SOOCH3. And then we have Cl minus. Okay? So then what happened here? You know how this is a very good now leaving group. So this leaves, then the chloride attaches. So, okay. Okay. Then the second step, it says CH3CO minus. What does that mean? CH3CO minus. This is step one. Step two, they add CH3CO minus. Do you see that or not? Mm-hmm. So what kind of compound is that? The base. So what is it going to react with? So it can react basically to this part, but it's not really the major thing. So your sulfonyl chloride here, if you add CH3CO minus, this is not strong enough to do a substitution reaction. You're not going to have a substitution here. So what it'll do is it can take the H and the sulfonyl chloride becomes sulfonate, which is very stable. So it's mainly almost like a distraction, because over there, see how we start with neutral, but you add something negative, you can end up with something negative. You understand what I mean? If I added something negative, I have to end up with something negative. So that part is really just on the side. Now, why are they using here? What could be an alternative for this? This is a substitution. So the alcohol turned into an alkyl halide. What would be another alternative if I want an alkyl chloride? Could I produce that product with a different reactant? What is it? Pyridine? Pyridine is not a reactant. Pyridine is there to neutralize things. Right. Okay. So here, that base is the role of pyridine. Okay, the CH3CO minus. But I'm talking about how do we get that same product without using the sulfonyl chloride?
Zinc chloride. Zinc chloride. And then pyridine.
Or we can use HCl. So what is the limitation for these two? The other two, they don't produce such a good leaving group. So that's why this is the best method, because it will give you a higher percent yield. To correlate it to the lab that you did, you all used some acid, chloride, and the yield was very low. If you wanted a better yield, especially for primary alcohol, you have to use this type of reaction. Is that clear? Do you understand? Because this one is a very stable base. So what's the role of this? This is the pyridine, like the role of pyridine. So pyridine is a weak base. This is also a weak base. Okay, acetates are weak bases because acetic acid is a weak acid. You agree? So it's a weak base, and that's pretty much what it is. And again, the reason I picked this is because I know you didn't see it in the lecture, but I want to understand how to think about these things. Okay? Next one, we also have primary alcohol. It's CH3, CH2, CH2OH. Is the same one?
There's an extra
It's another extra, yeah. And then we use PbR3. So it's similar. This and PbR3 are both Lewis acids. That's what I want you to think of. Whenever you see a substance, decide, is this a Lewis acid or a Lewis, or is it an acid or base and what type? So what's the first step? And this leaves. So what we get is CH3, CH2, 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 OH plus, and then PBr2. Now, in this scenario, it's the acetate that neutralized the leaving group. But here, what do we need to do first? They put pyridine, so here the pyridine will be reacting. We'll take the H, and this opens, and you get CH3, CH2, CH2, H2O. Is that correct? And then we have Br minus. So which step is first? The pyridine going to deprotonate, or we're going to have Br minus add first? Pyridine deprotonates first. So you see here, it's the other way around. You have the leaving group leaves all of it. This is different. So now the Br attacks this leaves. Okay, so you end up with CH3, CH2, CH2, CH2Br. And then we're going to have O minus PBr2 and the pyridinium ion. So what's the last step? Very good. Deprotonation of the pyridine. So these two will give you OH, PBr2 and pyridine. So we're going to do it so many times that it will become like easy. That's the reason I say please do all the questions that you have the answer for. The more you do, the better you get it. Okay, next one is the secondary alcohol. No, it's still a primary alcohol. And as you see, primary alcohols, it's always a good idea to use this good leaving group instead of just like we did in lab where we had very little percent yield. This is the way to do it, using a Lewis acid rather than a Bronsted acid. So we have CH3, CH3. Is correct, or did I miss? No, that's good. So the first is para-toluene sulfonyl chloride. So sulfonyl chloride is always, I will start with chloride. Sulfonyl is this. And then toluene is this. By the way, even though I didn't teach nomenclature, you're supposed to know how to name compounds. Okay, so naming is part of your test. Okay, so what's the first step? Again, we have here a Lewis acid. So we have to show an empty orbital. Everybody understand that little box that it's an empty orbital? And the oxygen docks there, the chloride leaves. It's always like two things happening. The oxygen takes the empty orbital and the chlorine leaves. It's mainly because of steric hindrance, it's too crowded there, so one of them kind of takes off. Then we end up with CH3, CH, CH3. And then plus Cl minus. So now the Cl minus is ready to attack. Okay, and then we end up with CH3, CH, CH3. And then the second step, you add a base. See, that one is the conjugate form of phenol. So phenolate. So both of these, this is acid, this is base. Why does this happen? This is pretty stable, you agree? Why is this stable? Resonance. But the sulfonyl is a better, more stable than this. So you have to add a second base to stabilize it. So I'll show you why it's better. So this takes the H, this is removed, and then you end up, so it's always, the last step is always between the products. So you're gonna end up with phenol, which is still conjugated, you see? So it's still pretty stable. And the sulfonyl is also conjugated. So this is a better deal for the sulfonyl to be a sulfonate than to be with an OH. Okay? So this is more stable than, and this is still stable because it's also conjugated. So that's your product. So every time you use a sulfonate, alkyl sulfonyl something, the first step is protonation, it's the lowest acid reacts with OH, and then the second step is the halogen attacks. But then you don't have the deprotonation first. So when you see pyridine, you have to deprotonate before you do the last step. So the last two steps switch if you see pyridine. Okay, that's all you have to remember. Pyridine is a base, so it will react on the protonated alcohol, whereas here, the protonated alcohol is going to stay protonated until the halogen attacks. Okay, next one, we have butanol. And we put sulfuric acid and heat. So what does it mean, sulfuric acid and heat? Sulfuric acid is a Bronsted acid. So we know for sure we're going to have what? Protonation, for sure. Okay? So we're going to bring sulfuric acid. So we're going to have protonation. But then it's heat. So what does heat do? Elimination. So what needs to be eliminated here? Whenever you have an elimination, you have to eliminate two things. You agree? Can I just eliminate the water? Why not? What do I get if I eliminate the water? Which one? Is that good?
No.
So what we need to do is, we have an H here. Okay, so what happened is the sulfonate will grab pH, and then this folds here, and this is. So every time you see heat, you have an elimination. And it's always you need an alpha hydrogen to create a double bond. So you end up with CH3, CH2, CH, CH2, plus H2O, plus sulfuric acid. So from this question, remember, when you have sulfuric acid and heat, especially with primary alcohols, you're going to have elimination. So acid and heat always gives you elimination. Okay? Next one is E. So you see here, we pretty much covered all the reactions of alcohols, but we did the primary. If this were tertiary, what would happen, for example? Probably every time you use a Bronsted acid, you're going to have what? Carbocation. So that's the difference. Okay, if you have Bronsted acid, like sulfuric acid, the first step here would be a carbocation and then elimination. So let's see E. Okay, so for E, we had so what is this compound? It's an epoxide. And notice, I always write my lone pairs. The book doesn't show lone pairs, and I think part of it is probably the software they have to use that doesn't always write the lone pair. Out of laziness, maybe, I don't know, but it's important to write your lone pairs. So we have an epoxide here, and we're adding a base. So we're adding CH3O minus. We know that epoxides have 3 atom ring, which means what? Ring strain. So they will always open. So every time you see an epoxide and you put a reactant, you're going to open that epoxide. The question is, how is it going to open? In this case, is it going to open this side or this side? It all depends on whether we're working with the base or with the acid. If we're working with an acid, what's the first step? It's carbocation. You understand? But if we work with a base, we don't have a carbocation. So can this base approach this carbon? Why not? Steric hindrance. So when you work in a basic environment, it's steric hindrance that matters. When you work in an acidic environment, it's the carbocation that matters. So here, this is going to have a hard time finding its way through this corner because it's full. So what's going to happen is this comes on this carbon and the oxygen takes the pair. So we end up with CH3, CH2, CH, OCH3. Write the CH3 down here. And then we have a C O minus CH3 CH3. That's your first step. Now what is the next step? They put CH3O minus and then they put CH3OH. So what is CH3OH gonna do? You're gonna have an H, CH3. What are we gonna have? This takes the H, this opens. And then it started again. It starts again. So if they put CH3OH on the arrow, it means you need it. Don't stop at just the first step. And as you can see, the CH3OH is the solvent probably, but it's also a catalyst. So it's going to give you the product, and then you're going to start again with the next molecule. Is everybody understanding this? Now remember, if we use a base, this has to attack, but it's bulky. So we can't attack on the most substituted site because it's too much going on here. It's really just because of steric hindrance. Okay, that's the only reason. But if it's an acid, it's a different story. That's what we have next. So the next scenario is, what if we use an acid? So the same epoxide, and we're going to use an acid. So here, the acid is hydrochloric acid. So what does the acid do? Always, Bronsted acid always protonates. So epoxides or alcohols, they always get protonated. Now, what happens next? Carbocation. So this opens, and you end up with CH3, CH2, CHOH, and then C plus, CH3, CH3. So now, what happens next? What's else in there? It's the chloride, but there's also what? What did they put? Methanol. So which one will attack the carbocation? Is it methanol or the chloride? Methanol. It's the solvent. It's a large excess. Even if they don't say it, you need to assume it's the solvent. So what's going to happen, and you'll see it why it makes sense. There's methanol here. What's going to happen first? The methanol will attach to the carbocation. Now here it can attach. Why? Why we have less of a problem with the steric hindrance? It's open because it's trigonal planar. The other one was tetrahedral. That's the reason. So hybridization is important. In here, you might say, oh, it's still bulky. No, even if it looks bulky, it's flat. So your substituent can attack from the top and from the bottom. So you have here CH3, CH2, CHOH, and then we have COH plus CH3, CH3, CH3. So what's next? Now the chloride will come into the equation. So the chloride can deprotonate to produce what? The hydrochloric acid, which what we need for the next mole. So you end up with the you see? So the difference between these two, on the top, the OH added to the terminal carbon. On the bottom, the OH added to the one before the last carbon. So it's different product based on their position. So everybody understands this? If we're using your base, the base it will always add to the least substituted because it's too much space there, too much steric hindrance. But if you add a protic acid, you're always going to get a carbocation, and that gives you the product on the last carbon. Okay? Last one here is an alcohol with SOCl. So this is pretty much covering all the reaction of alcohol with different Lewis and Bronsted acid. Okay, so the alcohol is primary alcohol. And we're adding SOCl2. SOCl. Okay, so what happens first? SOCl2 is a Lewis acid. So my first step would be this and this. So every time you have a Lewis acid, the halogen must leave. Remember, it's not like protic acid, only the H plus attached. Here, one attached, one leaves, always. So you have CH3, CH. Cl minus. So what happens next? Pyridine. So here, pyridine comes in. Grabs the H. So now, this is slightly different from the previous one. Here is the chloride attacks. This holds here, and this takes off. Okay? Why? Because the SOCl2 will produce SO2 gas, which drive the reaction completely to completion. So it's CH3, CH. And then we have Cl minus. So the Cl minus will be with the pyridinium ion. And the pyridinium ion will give its hydrogen to the chloride. So these two will produce HCl plus 3. So SOCl2 is one of the best because it really drives the reaction to completion. So slightly, the only difference here in the previous scenario is this opens, but in here, to open this literally, you have to form SO2 and the other chloride. So we did this in class, but this is the second time. Hopefully you do it more times. Okay? Next question that is similar to this is number 63. So we kind of do a similar question. Then I'll go back to some others. Any questions so far? Is everybody clear with this? Okay. Question number 63. We have an ether. Okay, that's, as you can see, 63 has a combination of many functional groups, so I liked it because it kind of covers more of the chapter. So I have CH3. And then CH2. So this is an ether, and we add a halogen. So what should happen first? Protonation, absolutely. Because that's the only possible thing to do. We have a low, an acid with an oxygen. So first step is protonation. Now, the bond must break, okay? If it breaks, we have to replace it with Br minus. Remember this? Br minus has to add this. The question is, which side, which bond will break? See, these two are identical in terms of polarity, you agree? So in terms of polarity, they're the same. So they technically should break the same proportion. But what's going on here? For sure, it's really what? Bulky. So will the bromine be able to come to this carbon? No. We don't have a carbocation. If we had a carbocation, absolutely. But there is no carbocation here, so the bromine is going to have a hard time getting to this carbon. You agree? So where is the bromine going to do? It's going to go to that side. Okay? So the bromine attacks this, and now this opens. So we start with an ether, we end up with an haloalkane and an alcohol. So that's called the cleavage. That's how you break the ether. You have CH3, CH3, OH plus Br, CH2. So everybody understands this? One of the two bonds needs to break. Which one? It's really because of stereochemicals. Okay, next one is B. B is the same, you agree or not? Take a look at B. Which side is the iodine going to add? The OCH3, which is less bulky. So we don't have to do this one. Yes?
I thought with heat there was elimination.
No, for ethers. These are ethers, they're not alcohols. Good point. Yeah, I mean, it's easy to think of it that way, yes or no? You're right, but these are ethers, they're not alcohols. Okay? Good point, very good point. Okay, C. For C, we have an alcohol. I'm going to write it in a different position just because of the four. And it's CH3, CH2, CH2OH. So this is a primary alcohol, okay? And we're adding chromic acid. What type of reaction is this? H04. So it's an oxidation. How far will it go for primary acid, for primary alcohol? It goes all the way to carboxylic acid. Okay, so it's CH3, I'm sorry, CH2, COO. Now remember, there's no mechanism for oxidations. Okay, so if you see an oxidation, just give me the product. And for all the ones I show a mechanism, you have to know all these mechanisms. We good? So far, so good? Okay. The next one is alcohol here. Yes.
How can you tell if something is supposed to be oxidized?
It's the reactant. Chromic acid is an oxidizing agent. Okay? So you have different reactions for oxidation. If you want to look at page 505. So page 505 on the top. And also page 501. I'm sorry, 501, 502. See 501, 502, the last part of the 501 and the beginning of 502, it has all the oxidation reactions. You see it? So it's chromic acid, it's PCC with CH2Cl2, it's NaOCl. So if you see these three, probably an oxidation. Okay? So here we have sulfuric acid and heat. So sulfuric acid is that substitution. Can we have a substitution of sulfuric acid? We can. You have a question?
For 63A, wouldn't it be an SN1 reaction?
It's an ether. It's not an alcohol.
Yeah. I'm looking on page 477. It's showing the mechanism for ether cleavage.
477,
Yes.
okay?
And then very similar, that is B on 478. It says it would be an SN2 type reaction. No.
Oh.
It's different because of where the bromide. was.
Well, it's still a cleavage, by the way, but it's okay. Yeah,
It says it's, it detects the less.
yeah, so I'll,
That's the same. So that's part B.
yeah. Okay, I'll go back to it. Just give me, thank you. Okay. Should I go back to it right now or do the D and then come back? We can do it now, so yeah, so. Thanks. So, yeah. So here's the answer why. It's very, I should have thought about it. So this is, when you have an OCH3, so I'll give you two examples so we don't make that mistake again, okay? So if I have an HBr or HCl or whatever it is, okay? It's not this molecule that we have in A. But it doesn't matter.
Yeah.
It still doesn't matter. So I'm gonna give you two examples, okay? So this one, the protonation is correct. So we have to protonate no matter what. But the difference, and I'm sorry for this, and I'm glad also that we made that mistake because then we will remember. In here, in this particular case, this will break before you add the bromine. Why? Why will this break? Tertiary carbocation. So that was my mistake. So if you're gonna get a tertiary, the carbocation always forms. Okay, ether or alcohol. Okay, so you have to form the carbocation first. So this definitely forms. And then you're gonna end up with the alcohol on the other side. And now at this point, then the bromine will add, the bromide will add. Thank you. Now I'll do the other one where it's similar but not exactly the same outcome. I'm gonna give you two because, so this will of course give us the halogen, the haloalkane. So what did we learn from this question is if we're gonna produce a tertiary carbocation, we're gonna have a carbocation before we even add the halogen.
And then since there's heat, would the bromine eliminate the alcohol
No.
that was produced?
No, here this alcohol, no. And it depends on how much heat, so, you know, but I wanna show you what would be the scenario where we want to have this, where it's bulky. So I want you to also see that. So did everybody write this down? Because I'm not gonna erase it, I'm gonna modify it. You got it? So now let's say here, I have a CH2, CH3. Do you see? In here, can we produce the carbocation at this step? No. So what's going to happen here? First step is definitely protonation. But in the second step here, you can't have a carbocation unless there is a methyl shift or hydride shift. So remember, if you can do a shift to get a tertiary carbocation, you will have the carbocation first. But if there is no possibility of tertiary carbocation, then here the bromide will come. And then where is it gonna go? Is it gonna go on this side or on this side?
Less bulky.
Why? Because it's less bulk. Okay? So then this attacks here and this bond opens. So even if it looks primary on both sides, this side is less bulky, so you get different outcome. Okay? So you end up with CH3, 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 CH2OH, plus, you can have a metal shift here also.
Yeah, that's what we're
So I
talking
should
about.
put another carbon just to avoid that. Yeah. No, but you can't have a metal shift on the primary. Right. You have to have a secondary, so there's no possibility. So only if you have secondary do you have a metal shift or hydride shift. So I was right. Okay, so you have this plus CH3, CH2 here. Yes.
If it's CH3, compound was replaced with just a hydrogen, would it be a hydrogen?
No, it has to be this one, that's what they were saying. If this one were secondary, so if I have a methyl here, then I can have a methyl shift. Do you understand? Because this would be secondary carbocation. You can't form a primary carbocation. There's no way. Even if you can shift something to make it stable, it won't help. So it has to be only secondary carbocation will do this shift. So I can give you an example. You want an example with the secondary carbocation?
Sure.
Okay. So here, very easy. All I have to do is put here an H. Okay. Put an H here. And a CH3. Okay. So what's going to happen? So that attaches, and then we have a CH, CH3. So here, OH plus CH2, CH3. Now in this case, you can form a carbocation. So what happened, this opened, okay? And then you have a secondary carbocation. So what happened here? This is secondary. We will have a hydride shift. Then you're going to create this carbocation. And then the bromide now will attack. So this is the scenario where you have the hydride shift or methyl shift. It's always when you have a secondary, not primary. Okay, you can never do the shift, even if it looks like it's possible. It's not going to happen unless you have a second. Yes.
Part B, I think, is also different, in that it attaches to the more hindered side because of the good leaving group that the methanol produces. Just that.
Which part?
63B. What was B? Because originally it was the same. I think it's in the K.
63B is primary, so it's not a tertiary. And it's not a secondary.
Yes. Oh, so which side would the iodine,
Will attach
Attach
to
to.
CH3O
it wouldn't go to the other side
No,
because
because it's too bulky.
the methanol's good.
Yeah. The
It's not
CH3 is less bulky than all the other parts. We already did B. Did we do B or not?
Oh, yeah,
No,
okay.
we skipped it because.
But you
it's a
understand this,
connection.
guys? So everybody understands, if it's tertiary, you're gonna form the carbocation for sure. If it's secondary and you can do a hydride shift, then you do that. Hydride or methyl shift, then it will form a carbocation. And if it's primary, no carbocation, no matter what, okay? No carbocation. So let's do that. B isn't primary, okay? You got this? Okay? So D has and we have these ones. So first step,
The right side's a methyl group.
thank you. So the first step is coordination. Now, which side will open? You have an iodide. First of all, here, there's no way to form a carbocation. You see that? Whether I open on this side or on that side, they're both what? Unstable carbocation. So it has to be an SN2, not SN1.
Oh,
So,
You have an extra.
part B, it's not, the beta is tertiary.
You have an
The
extra,
CH
you have an
yeah,
extra
yeah.
methyl.
Yeah. The left side has an extra methyl.
The
It's
top one.
just
So it's just
CH3,
CH3,
it's okay, even if I don't put a CH3, either way. Whether with an H or CH3, you get the same outcome. Why? Because this side now is bulkier. You have a lot going on this side. This side is less bulky. Even if you think it's gonna attach to this, but because of the free rotation, this stuff will be interfered.
Even with the right side being a methoxide, it's, and being a good leaving group.
Here we are, both of them are, it's not gonna be a methoxide, by the way. It's gonna be a neutral substance, so it's very good leaving group because it's neutral. Whether it leaves on this side, it's an alcohol. The leaving group is an alcohol, which is very stable. Okay, it's not a base, it's an alcohol. So what's gonna happen here then is this comes here, this. Is that correct? No, which side would the iodine go?
It goes on the right side.
On the right side, why?
Less
Less
hindrance.
steric hindrance. So this goes here, this goes. Okay, so you end up with CH3, CH, CH3, CH2, OH. So you see, this is very stable, it's not an anion. And then CH3I. So now let's go back to D. So for D, we have sulfuric acid and this compound that I'm going to write in a different position. And we have two methods. So we bring sulfuric acid It's always, no matter what, it's always gonna be protonation. Every time you add protic acid or Bronsted acid, you're gonna have protonation. And then this opens. So it's always gonna be protonation. Now, what happens here? If this has to open, if this leaves, what are we gonna end up with? Secondary, and what happens when you have a secondary? Rearrangement. So we're gonna have here a secondary rearrangement before we can have elimination, because it is gonna be an elimination, okay? So first step, this goes out, and you end up with this. And then we're gonna have methyl shift. And then this is now the positive. And then what happens next? We have to have an elimination. So what gets eliminated here? A hydrogen. Which hydrogens will be eliminated? How many possibilities we have? We have the hydrogen here. Where else? We have hydrogen here and the hydrogen here. And they will all eliminate. So we're gonna end up with how many products? Three. Okay? So I'm gonna put each one of them in a different color. So, yes, sir.
They're not.
I'm not talking about this, here,
Oh, okay.
okay? The hydrogen here, the hydrogen here, and the hydrogen here. You agree? So we're gonna write the three of them. And I'm gonna use different colors for each one, so we see what happens for each one. So the top one here, the red. Then I'm gonna put the green one here. And then I'm gonna put the magical colors. I'm gonna use the orange. Okay? So how does it work? I'm showing you in one of them, but you understand for the others the process. So it's the OSO3H. That's the base. That is the one that's gonna grab the H. So this folds and produces, I'll use the red for this one. So this one, this takes the H and this folds here. So the red will give us this. See it? Now let's look at the green. The green, this takes the H, this folds. So the double bond for the green will be right here. We have methyl and a double bond. And then the orange, this attacks this, this folds here. So the orange will give me this. This, and a double bond. Yeah,
Are any of the three favored maybe due
excellent, that was my question
to
next.
constituents?
So my next question is, we're gonna produce 3 products. Which one is the major one and why?
The second one.
Middle
is
one.
most stable.
Absolutely. So this would be the major product. Why? Because it has 4 substituents on the double bond. Which one would be the minor one? The green one. Okay, so this would be the So when you have elimination, be careful, guys. First of all, every time we have a Bronsted acid, and there's always gonna be a carbocation if possible. That's what we learned the hard way. Second thing is, when you have elimination, look at all your options. There's more than one option. Okay? Next one is E. We already did E. What do you think is gonna happen for E? We did it the same in the previous one. I'm not gonna write the whole mechanism, I'm just gonna give you the product. But we did the exact same thing, believe it or not, in question 55F. Okay, so it's exactly same mechanism as 55F. And I know I put a few questions like this on your pretest, okay? Hopefully you tried them. Right now you should be on chapter 19, not on 10. If you're still on 10, you're in deep trouble. I tell you. Okay, so I like to write it this way and put my epoxide now, honestly, this is just a distraction. You can replace it by method groups. Doesn't matter. And that's why we did exactly the same thing with here as the method. So what's the first step when you add HCl? We're working in an acidic environment, so what's the first step? Protonation followed by carbocation. So this and then the next step is we're going to produce a carbocation. Which one will break?
Or substitute.
Because this will become tertiary. So we have this. And now look, when this bond opens, we have a CH2 and then an OH. Okay? Really? No. We have a plus here. And then what do we do next? Chloride. So the chloride will attach to the carbocation. And you end up with chloride here and a CH2OH. The other one, with the base. So what happens here when you have a base, the first step is you break the ring. Which side will the base approach? Either this one or this one. This is pretty busy. So it's gonna go on this side, this open. Okay? So you end up with O minus, and then here, CH2, OCH2. Do you see it?
For both E and F, there is H3OH. Like that? Does that do anything?
Oh, yeah, thank you. So here, it's the same as earlier. So instead of now adding Cl minus, what should be added? CH3OH, thank you. You got that? Yeah, so it's still plus, I'm sorry, it's still plus, but and then here, OCH3, H, like we did earlier, exactly the same. This attaches, so you're going to end up with CH2OH on top, putting it out of my way. And then here we have OCH2 CH3. Is it CH3 or CH2OH?
CH3.
And then what's next? Now that's when the Cl minus takes the H. Because every time you see an alcohol there, remember it's the solvent. I didn't see the alcohol, thanks. So you end up with this. And in here, we're gonna have OCH3, and then we're gonna have HCl that does the work. So here now at this step, what do we do next? This is a base, so we have CH3OH. This is easier because now this is a base, this is an acid. This makes the H, and it regenerates the OCH3 to restart again. It's exactly like the previous question, exactly this. Now, if they didn't put CH3OH, we would just add the Cl, that's it. But if they put CH3OH, make sure you use that as the second reactant. Okay, next one is G. You got this? By the way, even if I don't finish them, you have the answer key for them, and you have very similar questions. I wanted to really do, which one? Yeah, I'm gonna do 83. So if you want to stay a little bit longer, for H, by the way, it's an oxidation and it's a secondary, so you're going to end up with a ketone. And J, we already did that, HBr, so if you're going to have a carbocation, which is, we're going to have a secondary, but there is no carbocation, so we already know how to do that. I'll do quickly G, and then I want to do the 60, which one did I say? 83. Because slightly different, that's all. Slightly, not much. So G, we have and when you see something like this, it means pay attention to stereochemistry. It's very important, okay? So that's the reason I wanted to do this, give an OH. Meaning this is in the front, it's a chiral center. They both are chiral centers. So first step is TSCl. So it's a tosyl, which means it's an SOOCl and something, like an R, anything on that side. Okay? So you can put it any substituent there. So that's what TSCl means. So what happens first, we know that this is a Lewis acid. So first step, this attaches this. So we end up with then what happens next? They didn't show it, but there's pyridine. So here, the pyridine will grab the H. Okay, so pyridine takes the H. This goes there. And then, of course, this reacts with Cl minus. You understand this part, period intake. The H from the Cl minus. The Cl minus takes the H from the pyridine, I should say. And then our pyridine is regenerated. And then the HCl. But then what's the second step? Okay, so this is step one. See how they put one? That's one. Step two, we're gonna start with this. That's your product, you agree? So step two is you get this product and you react it with NaCN. So step two, you have CH3 and we're going to bring NaCN. So what is NaCN? It's really Na plus and Cn minus. So I have a Cn minus here. Cn minus is a strong base. So what is going to happen here? What's the purpose of putting the 2-0 here? It's a very good, so it's going to leave. What mechanism is this? Can we get a carbocation? You understand we can't get a carbocation. Why? It's a secondary. Secondary stable? Only if it's tertiary you get it. Or if the secondary can rearrange. We can't rearrange here, and it's not a tertiary. You understand? So what's the mechanism if there's no carbocation? It's an SN2. So how does SN2 happen? Will this come on this side or the back side?
Back.
So it's back attack. So this has to leave from the front. But then what happens? It's an inversion of configuration. Remember? So if you have an SN2, there's always inversion of configuration. So what do we get? We get CH3. So this side, we don't touch it because it's not involved. Again, sometimes they like to give you some distractions, and that's just it. So every time you have an SN2, you have an inversion. So what happened next is you're going to end up with Na plus. There's an Na plus here. So this attacks, this leaves, but it's a back attack. You understand? So back attack means inversion of configuration. So you end up with Na plus and then an O, SO, R minus. Now, if this were a tertiary carbocation, what would happen here? And then you're gonna have attack on both sides. So how many products you're gonna get? And what is that called? Racemic mixture. Okay, so primary and secondary with no rearrangement, you're gonna only have inversion of configuration. But if it's tertiary, you're gonna have the racemic mixture. Okay, then I said, what time is it now? Okay, I have 4 more minutes. I can do it. So I wish if you could come early in the morning and I can do discussions of problems. In the previous semester, students come at 7. They really show up at 7. Now I have almost half a class. They show up at 7, I do this from 7 to 8. Yeah, they used to come but if only one person is gonna show up, it's not worth it. It's worth it for the person, but I won't be in the room. I'll be in my office. So here's the last one that I wanna do. So we have this. But you see the value of doing these problems, is everybody seeing this? So that's why. And I remember one of my students used to come from Rosarito and showed up at 7. Yeah. Now she's at Berkeley, UC Berkeley, because she was committed. Okay, so first step, what do we do here? Protonation. So it's automatic, I don't even have to think twice, you agree? And should I protonate this side or that side, either one is fine, okay? Both are equal. So, now what should happen here? It says sulfuric acid and heat. So what does that mean? If we heat, we have to have the water leave. So what should happen here? This will leave, you agree? But then we're gonna end up with what type of carbocation here, if it leaves in one step? It's gonna be primary, is this gonna work?
No.
So guess what happens? It will leave. This has to leave, but now this docks here.
Oh, there you go.
So this is called intramolecular reaction. You understand, in the previous one, we had the methanol come in. You don't have to have a methanol or anything. It can happen within the same molecule. The only condition is you have to have either 5 or 6 atoms. So how many atoms would be here if this leaves? 1, 2, 3, 4, 5.
Don't you have to use the negative sulfuric acid to remove the H first?
No.
So you have a
It
negative
won't,
oxygen
no, what's the point of removing the H?
on the other side to make it negative, so
No.
no rat.
No.
Okay.
No. You can't make it negative when you have an acid. You understand? If you have an acid, everything has to be positive. You can't use an acid to create something negative. Whenever you have an acid, the only negative thing is that anion, but you can't use the anion to create a weaker anion, a stronger anion. So here, we're gonna have this. So it's a 5-atom ring, and one of them is what? Oxygen. And it's gonna be positive. So what's my next step? My last step is, now I bring the SO3 minus, and then remove the H. And why can I remove the H here? Because I'm regenerating my sulfuric acid. You can't regenerate something negative, that's not what you started with. So you end up with this. So what does this show you? It's called, these reactions can happen within the same molecule. That's how we make cyclic compounds. And you have a couple of these on your pretest. We did it.
So Monday, 7 a.m.?
If you come at 7, I'm here. I'm here at 6:30.
All right.
So you come to my office and call me and say, hey, can you come to the room and let's do some practice.
Probably not.